Okay, so we know now that the average displacement from some starting point for something that you repeat many times, okay, is proportional to the square root of the time it took, okay, and also proportional to this constant we call d, the diffusion coefficient, and then there's just this factor of 2, okay, and that diffusion coefficient is defined as the length of a step taken squared divided by 2 times the time it takes to take one step. But because on a molecular level it's really hard to know that length, it's really hard to know that time, okay, then we can just collect those, make this definition, and this is something we can calculate, and we find it's a property of the material. Okay, so we've got all that. So our interesting thing is the average distance is proportional to square root of time. So that's one thing we now know. Now in 2 dimensions, all that changes is instead of a 2, you get a 4. In 3 dimensions, that becomes a 6. But otherwise, same thing. Okay. All right. Now we have another idea. If you take this and instead of repeating one experiment a whole bunch of times, what if you have a whole bunch of things and let them go at once? Okay, like for example, you take a drop of ink and you drop it into a glass of water. Okay, what can you say? Well, the thing is this whole idea here, in that case, the 3-dimension case, each molecule of ink is going to do the same thing. They're all going to follow this behavior. And so instead of looking at it like one at a time and counting their averages, we can actually calculate what the concentration of molecules will look like at a later time. And it's really interesting. If you take these ideas here, okay, and then you calculate it, we'll again stick with a one-dimensional case, we'll stick with just this one-dimensional case, you end up with a really interesting equation that's found to mimic, well, it's found to describe how dye will, or ink will diffuse in a glass of water. Also, how heat dissipates, let's say, in a room. This equation is called the diffusion equation, and there are other ones like the heat equation. It looks identical in form. It just has different ideas, more like temperature instead of concentration. Okay, but so we're going to focus on this. Where it came from is a little bit heavy on the math. We're not going to worry about that one. But let's try and see if we understand what it means. Okay, first of all, C is a concentration. So this side, change in concentration in change in time. It's kind of like a velocity in a sense. It's concentration velocity. How's the velocity changing in time? All right. So that's what we think. This is the value of C on a concentration versus time graph. So I've got one down here. Here's a concentration versus time graph. That A, I am representing what's the concentration of this point A over here. Okay. D, we already know what it is. It's a parameter that describes the material of the fluid. Okay. Now this is complicated. This is really complicated. All right. But there's a simple way to think about this one. All right. Basically, it's kind of like if we called this a velocity, this is kind of like an acceleration, but it's in position, not time. But this is basically the change in concentration twice. Okay. How does it change 2 times? So how does the change in concentration over position change over position? Now that sounds totally freaky, and I'll explain more. But the biggest thing we say, okay, forget the math here. What does it mean? It simply means the curvature on a concentration versus position graph. Okay, now I've highlighted this position and this time. We have 2 different types of graphs here. Okay, we have a time graph. We're kind of familiar with those from kinematics. Okay, that's like I highlighted here. Just how is the concentration going to change in time? That means we're looking at a certain point. Okay, X is fixed, like at this location A. This concentration versus position graph means we're looking at certain time. So, for example, at T0, we're looking at everywhere along our axis. Okay, and so a drop of ink very close to the initial time you dropped it in is going to look kind of like this. There's a lot of ink right where you dropped it and very little farther away. Okay, That's what a concentration versus position graph would look like. How much concentration depending on where you're at in the space. Okay, so what does curvature mean? All right, so let's go over here, all right, in this area. So this is an example of curvature. Okay, when you have a curve like this, which is very common, it's called a Gaussian or a bell curve. There's a spot called the inflection point that separates the curving getting taller and the curving getting smaller. Okay, this is called an inflection point. Basically, everywhere between those two inflection points, the curvature is negative, meaning it's opened down. So it's like opening up. It's like a bowl upside down. Okay? Now everyone outside of those inflection points is curving upward. It's like a bowl, and you can, hold stuff. It's in the right direction. It's holding. You can, if there's a bowl, you could hold something in it. Okay, so this is like a bowl being dumped out, and this is like a bowl being, you can add stuff to it. So if it's bending such that it opens upward, like this case, that's a positive curvature. Okay, negative curvature is if it opens downward. Okay, now let's understand curvature a little bit more. So something with big curvature, so this is a big number. Okay, something with big number. That means that it's a really tight curve, or in other words, it's not straight, it's less straight. Big curvature means less straight, okay? So it means it curves a lot. Whereas small curvature, this is a small number, means it's more straight, it's closer to a straight line. Okay, so this is an example of something with small curvature. This is an example with big curvature. Okay, so that's what this term means. And the interesting thing is, how does this come about? Okay, so if we understand what curvature means, we understand this is how concentration is changing at a point, okay, then we can see why it would make sense. So just imagine back over here, this drop of ink we just set in at an early time we'll call T0, okay? All right. Since this has a really tight bend, or it's very not straight, okay, it's less straight, it's got big curvature, that means this number is really big, which means this should be changing a lot. Since this is a fixed parameter, if it's ink and water, that's a fixed number for ink and water. It'd be a different fixed number if I was doing ink in honey, okay? So we'll stick to kind of ink and water. Okay, so this is just a constant. So if this is a big number because it's very tight curvature, that means it should change really fast. And so we can see that initially when I drop that ink in, it's going to drop, the peak of it is going to drop because more is going to go out. It wants to go away from that spot. Okay, and so it does. And so at a later time we get this. It is spread out and the peak's gone smaller. But now that curvature is smaller, okay? Since that curvature is smaller, it's still going to spread out, but just not as fast, okay? So the amount of molecules at that point will get less, but just not as fast. And similarly, so we get a later time looks like that, and a later time we're going to get this, and you can see that these vectors get smaller and smaller as time goes on because the curvatures are getting less and less. This number is getting smaller and smaller, which means this number should get smaller and smaller. Okay? Now, having said that, what about this minus sign? That minus sign is kind of it makes sense minus sign. If I put a lot of stuff here, I have a big concentration and it should get smaller. Okay? So if the curvature is big, I should get less concentration. So I want my concentration here to get smaller. So if this number is big, I want this to get smaller. The rate at which it gets smaller is big, but the amount is smaller. So it's going to get smaller fast. Okay, so that's why this minus sign is there. If I have something, if this is a small number, okay, or if I have a low concentration here, okay, and and the curvature is small, okay, it's still going to get smaller. That minus sign still is there. Okay, so it just gets less and less. So that kind of makes sense, at least I hope it makes sense, is that if you have a large concentration, okay, with a tight curvature, it's going to get less concentrated. It's got to spread out. So that's what that minus sign means. Okay, so there's a bunch of things we can do for this. First of all, just review. We've talked about this diffusion equation, okay, that relates where the concentration curvature is, okay, and how it changes in time. And we've talked about what curvature means right here. Okay, and we just kind of tried to explain how it's physically connected. Now, one thing to think about is let's focus at one spot here. Okay, so if I'm sitting here at A and I'm measuring the number of molecules or the concentration at that point, and I measure it as a function of time, that's what this graph is doing. Okay, so I measure the concentration at point A, okay, for time. Now, initially it's very small. Okay, some small value. But then, the T1 I get right there, and I get a larger value. And at T2 I get an even larger value. But as it starts to spread out, this gets flatter, okay? And assuming we have a huge container where we put the ink in, it's going to get really small. You're going to spread all this ink over the entire thing so it's not big anywhere. That means it's got to get smaller again. So in fact, if we're standing at a certain location and we drop a big blob of ink in the middle, okay, or in other words, that we have a big Gaussian peak, a tall, tight Gaussian peak, that means we're going to see a peak in time pass by us as it goes. So even though the peak in space just constantly gets smaller, at some point off to the side, it will get bigger and then smaller. Okay, so that's how we can kind of think about it.